So good morning. I'm going to talk about some of the architecture changes that the community, the Apache CloudStack community, has been planning and discussing to do. So hopefully that will give you an idea where CloudStack is going. This is still a very early market, and technology in many ways is still not mature. So lots of big changes are still happening. We'll show you the current architecture of CloudStack, and there's a lot of work going on to change CloudStack into a cleaner, more modular architecture. So when some of that work is done in a few months, I think CloudStack architecture will look like this. Users make requests through the UI or API. The requests will enter the API layer. Then it's checked to make sure that the user has the rights to make that API call. So that's the access control layer. Then the request is dispatched to the orchestration engine. Orchestration engine picks up the request from the job queue, because in many cases the requests take a long time to execute. So as the request coming in from the API layer, they're put into the job queue, and it's asynchronously picked up by the orchestration layer and executed. The orchestration layer coordinates a number of elements in the cloud computing environment. It manages the resources that exist in the cloud, and the cloud consists of a variety of resources, from hypervisor resources to network resources to storage resources. So all these resources are controlled by the orchestration engine through the resource management system. As Will explained earlier, there's a message bus in the middle whose job it is to transmit these commands to all the resources in the cloud, because in some cases these resources could exist in another data center, and the communication between the orchestration engine and the resources may not be 100% reliable. So the orchestration engine needs to make sure that it handles the failures that could happen between the time it transmits a command and the time it gets a response. So because commands can fail, what's really important for CloudStack is when we design these commands, we have to make sure that the commands could be safely repeated. It's very important to do that, because if a command, what happens is if a command fails, then we can retry the command. If the commands cannot be safely repeated, we may end up doing the same thing twice, and that could cause undesirable consequences. So an example of a command that could be safely repeated would be to start a virtual machine. That command could be safely repeated. Or a command that says, I want to stop a virtual machine. That command can be safely repeated, because if the first time it didn't stop, you try again, you can still stop it. But let's just say a command that cannot be safely repeated would be a command like I would allocate a new disks. Now, if you allocate it once, you get one disk. You allocate twice, you get 2 disks. But there'll probably be a way. There are ways you can make the command safer. Say, let's just say by maybe giving the disk a name. So then the command becomes repeatable. Because if you say, I want to create a disk with this name, and whether or not this command is successful, you try again. If the first command has not been successful, the disk will be recreated. If the first command is successful, then the disk with the name already exists, so the second time you ask for it, then the second time will fail, but in the end you will get just one disk. So it's very important to, when you design for CloudStack, you make sure you create commands that can be repeated, because the communication in a very large scale system, the communication can be unreliable. The orchestration engine contains some of the core business logic of running the cloud, but because it deals with so many different types of hardware, it has to be extended all the time. So the way to extend the capability of the orchestration engine without making big changes is by introducing a plugin framework. So if you, for example, the logic of dealing with storage should be in the orchestration engine. But the logic of how the storage behaves, whether it's NFS or object store or iSCSI, that should be a plugin. So plugins are like device drivers in an operating system. CloudStack also has a fairly unique, this is actually one of the most important part of CloudStack. It's very unique that it supports a system VM framework. So I'll explain a little bit more about system VM later, and we'll give you a demo of the CloudStack. We can probably also show you some of the examples of system VM. In the cloud, there are a lot of tasks that need to be carried out. For example, if you want to copy some data from one data center to another, you need a process to copy that data. And the question is where you want to run that process. And the way CloudStack does it is it actually create a system virtual machine and hand it the task of copying that data. And these tasks could be pooled together. So if there are more tasks, more jobs that needs to copy data that's needed, then we can create more system VMs to handle the workload. So if you know about CloudStack already, you know terms like VR, virtual router, terms like secondary storage VMs, SSVM, or terms like CPVM, console proxy VM. These are all examples of system VMs. So we'll show you. The question is, what's the difference between the current architecture and this architecture today? I'd say this architecture that we're going to. So this is an architecture like this has always been our goal, but today we don't fully conform to this architecture. For example, the access control layer is not very well refactored. So this layer, although this layer, if you look at the code, it's spread all over the place. It's not cleanly separated out. And some of the tasks that should be part of the plugin framework today are not well factored out in the plugin framework. And the system VM framework itself is also not particularly clean. So I'm going to talk about some of these areas that we need to make improvements. Okay? So yeah, so you're right. Your observation is correct. Even the architecture diagram that Will presented before was somewhat similar to this, although it is not exactly the same. Will presented. Oh, you have a question?
さっきの図のところで、一つ前のアクセスチャンネルのところで、メッセージバスのところの、要は下のところとに新しいフィーチャー、いろんなものをつけるということは開放されることになるんです。それは多分メッセージバスのプロトコルが開放されて、リソースマネージャーにそれが通知するやり方が多分開放されればできることになると思うんですけど、ちょっとそういうのは考えられてないのか。メッセージバスの下に新しいリソースを付け加えたりとかっていう。
So the question is whether we want to add new resources under the message bus. Is that a question? The new resources are always being added. For example, CloudStack used to only support a very limited set of firewalls and load balancers. And now a lot of partners are adding new models of firewalls and load balancers into CloudStack. And CloudStack used to only support, used to not support Hyper-V, and now Hyper-V work is going on. So those would be considered new resources under CloudStack. All that work, a lot of that work is not done by Citrix, it's done as part of the Apache CloudStack project. So 100% of CloudStack work is open source, part of the Apache CloudStack project. Okay, thank you. We'll explain the current storage architecture with primary store and secondary store. And going forward, there'll be some changes. The big change around the primary storage is to really make sure, because today primary storage is only valid for one cluster. And going forward, because a lot of customers, they want to utilize features like storage migration. And capabilities of EBS, Elastic Block Store. There are lots of vendors, like in Japan, there are people like VA Linux that's been developing Elastic Block Storage technologies on Hitachi that we're able to incorporate. So we want to make sure that primary store can span the entire zone, not just one cluster. The secondary storage side, really right now we have a challenge because secondary storage today is a performance, is a scalability bottleneck because there's only one secondary storage per zone, and as the zone continues to grow, it was difficult for secondary storage systems to keep up. And going forward, we are basically dropping the notion of dropping the concept of secondary storage. And we're moving to a true object storage system. Object stores are designed to scale much, much wider. they're designed to not just scale for the whole zone, but they can scale for the entire region. Object storage systems are essential to implement Amazon-style cloud. And in the early days, a lot of the customers didn't realize that. They use Amazon-style cloud like a virtualization system, just as virtual machines. But today, more and more people realize in order to write applications that can withstand the failure of an entire availability zone, they need to store the data in the object store. Otherwise, if they keep the data inside the zone, they will lose the data with a failure of an entire zone. So one of the most exciting developments that's going on is the close collaboration between Apache CloudStack and Apache Hadoop. And the way this collaboration is happening is users are very interested in using Apache Hadoop as object store. Hadoop is much more than an object store system, but at a very basic level, Hadoop is a distributed file system. HDFS is a distributed file system. It's a distributed file system that's derived from Google's own distributed file system. It's the open source implementation of the file system technology developed inside Google. And just like CloudStack, it's also written in Java, of course, Apache license. So we're very excited about the potential of using Hadoop as the object store solution for CloudStack. Now, the deployment architecture that Will explained earlier is also going to evolve. Today, to deploy CloudStack, this is actually a one deployment of CloudStack with 2 regions. So if you know about Amazon, you understand the regions. Regions are geographically separate cloud installations. So Amazon, for example, has a Japan region and a Singapore region. Communication between different regions are expected to be expensive. And then within a zone, you have multiple, within a single region, you have different availability zones. And different availability zones, they are expected to be maybe in different cities, but they're not expected to be very far apart. So for example, Amazon availability zones in Japan, I think are all clustered around Tokyo. But they're still separate enough so that if one zone fails, say due to an earthquake, it's possible, it's likely that another zone will continue to run. So that's the idea. And today, CloudStack management server cluster, a single CloudStack management server cluster is required for each region. So that means a management server cluster has to sit inside one of the zones, and it controls all the availability zones inside the region. And the problem with this is, of course, if the management server cluster fails, then you would lose. Even if this one zone failed, you would lose the management server cluster for the whole region. So to deal with that, our customers set up a standby management server cluster in another zone. But it's just a code standby, and when failures happen, the admin has to manually bring up the other management server cluster, change over the DNS, and perform the disaster recovery operation. So going forward, it's going to be different. What's being discussed right now is that going forward, we will have a separate management server cluster zone. So the advantage of that is failure of an entire zone will not only not impact the running of virtual machines, other zones, but it would also not impact the running of the API in another zone. So these other zones will not be impacted at all. Since going back to this gentleman's question earlier about the rest of the slides, going to talk a little bit more detail about some of the architectures enhancements we'll be making. One of the things that the orchestration engine has to do is it has to do very regular state management, because when it orchestrates components, things have to fail all the time. And if an operation fails, it has to have a way to recover from that. And that involves fairly sophisticated state management. And right now, that state management has been implemented in certain operations, but not other operations. So this would, I think we have to improve the state management, the state regime implementation for all operations inside the cloud orchestration engine. And that would involve some more work. Right now, the cloud orchestration workflow is fixed. There's no, basically creating a VM involves doing a set of things on storage, on networking. Maybe you touch a few other elements, but that flow is canned, it's fixed. So there's been some interest in how we can make that flow customizable. That could involve a workflow engine. And lastly, like I said, the plugin framework needs enhancement. Particularly, I think today the networking plugin and hypervisor plugin are in pretty good shape, but the storage plugin it doesn't really exist. So we need to make some changes to actually implement the storage plugin framework. So there are different storage plugins that be implemented on top of that. Like I said, in CloudStack, system VM is a very cool idea, because the fact that we can run all these complex business logic in system VMs automatically, without the user having to deploy them and configure them, really simplifies the installation and operation of CloudStack. But there's actually been a lot of discussion about potentially we expose that system VM framework to maybe third-party VMs, not just virtual machines, not just flow that exists in CloudStack. Maybe even a user VM are able to use some of these system VM services, like AutoScale. Like when the load comes in, we can just increase the number of VMs that's running. So system VM, this is if you guys don't know what, some of you don't know what system VM is, I just want to explain the role it can play in CloudStack. So this is one way we could implement an object store solution, a backend object store like Hadoop or NetApp. Because what happens is, whether we use NetApp or Hadoop or other object store systems, it's possible that these solutions don't implement the exact S3 API that we want, right? So we need to run an API proxy, which takes S3 API requests from the web and then translate it to the native API that's supported by the backend store. But the question is, where do you run that proxy? And I think a great place, you could allocate some dedicated servers to do it, but that's complex, and you need special servers just to run these proxies, so that it adds to the admin overhead. But the great way to do it is to use system VM. And the great thing about system VM is they can scale. If you have more API call coming in, we just start up more API server VMs, and then the load could be met. So again, as I explained in the beginning, there's some work we still need to do for the API server itself. We need to clean up access control code. Right now, they're quite messy and they're not easy to maintain. And another idea is we can potentially just run API server. I already explained, S3 could be run in the system VM, but maybe even the entire API server could also just run in system VMs. So that reduces further reduces the computational power that's required to run the management server. So today the management server is already quite scalable. A management server, we tell our customers each physical host that runs management server to manage 10,000 nodes, computing nodes in the cloud. But if we move API servers out, we're essentially moving the API server workload from that one management server to 10,000 computing nodes. It can now run on any one of these 10,000 computing nodes as a virtual machine or as a group of virtual machines. Right? So that's going to make scalability much, much higher. VM sync is another area that requires improvement. Today, CloudStack has a technology called VM sync, and it's designed to enforce the desired state of the system that's stored in the CloudStack database, and it's designed to enforce that to all the nodes, all the resources that's being managed. So today, the way CloudStack works is we get an API call, and we basically said this API call wants us to do this, and then we just save that into the database. Now, like I said earlier, these operations, then we try to go out and through the message bus to control the resources. But like I said earlier, these resources are, these message buses is not always reliable, and that's why these operations have to be repeatable. So CloudStack does all of that. CloudStack will keep trying until the actual state of the resources matches what the desired state in the database. But we've actually realized that's not the right thing to do. Even though it seems like a very common thing to do in the cloud, like most of the cloud management systems are designed this way. A big problem with this approach is we cannot interoperate with other management tools. So a lot of our customers have told us they like CloudStack, but they would like to continue to use, say, VMware vSphere, vCenter. They like to use ZCenter. They like to use Microsoft System Center to continue to manage the virtualization cluster. So now, what's going to happen is if a user goes in and they modify something, then VM sync is going to enforce the desired state, and what the change admin made will be overwritten. Right? So, and there's another downside is this desired state model is it works when there's no bugs, but if there's a bug, then what if CloudStack propagates the state to a very large cloud? What if it propagates the wrong state? So that can cause a very big outage. So we're actually changing this to a different model, where CloudStack no longer enforces desired state. It would issue commands, but then it would choose to synchronize with the real state of the resources. So it's really a different model. With that different model, it allows us to function in a different way. So this is how CloudStack functions today. The users come in, the admins come in, go through the CloudStack management server, and then they manage the backend resources. So with VM sync, this is the only model that works. But if we make VM sync work a different way, where it can work with, it no longer enforces desired states, then what can happen is admins can have other options to manage the virtualization cluster. And that's what a lot of our customers, a lot of our users are asking CloudStack to do. CloudStack needs to play better, needs to work better with the existing management solutions out there. CloudStack cannot assume we're the only management solution for the data center. But CloudStack can still add a lot of value, and if we did do that, we actually going to make CloudStack more useful, because now what can happen is it makes it a lot easier for customers to register their existing virtualization cluster into CloudStack. So today, if you go to install CloudStack, you actually have to wipe out you have to configure the virtualization cluster in exactly the way that's demanded by CloudStack. You cannot take an existing vSphere installation and then just have CloudStack manage it, because the model that because the configuration that already exists in the virtualization cluster will be wiped out by CloudStack. But with this different model, CloudStack can simply assume the responsibility of managing existing clusters. So what's going to happen is, you can have a CloudStack, but then it's very easy to extend the reach of CloudStack by adding the existing virtualization components you already have. And that's what we're seeing with customers, because our cloud is growing, but it's growing from a very small base. Most enterprises, they still have, say, 10 servers, 20 servers, 100 servers running as part of the cloud. But they already have, in many cases, thousands of servers running under server virtualization. So if we make CloudStack more flexible in being able to incorporate existing clusters and then add value to that, we can make cloud grow much quicker. So that's all I wanted to cover in terms of architecture enhancements. You have a question? Go ahead.
ですね、ランチの時間が決まっていて、12時半からになるんで、質問はランチタイムとか、あとは、午後からもQ&Aタイムがありますので、そちらでお願いしたいと思います。